In the form f of x equals a times b raised to the x. Now remember, we have had linear functions, quadratic functions, radical functions, rational functions. This is just the next function in line. Now, we have used exponential functions. We have looked at the parent function, and we usually use 2 raised to the x so that we can actually put it into our calculator. So let's look at this model of f of x equals a times b raised to the x. Now, the a, this is what we call the initial amount. Now, in other words, whatever the word problem tells us that we are starting with, that number is going to go in place of a. It's the initial amount of the problem. Now, the b, do not confuse this with our horizontal stretch and compression. The b in this situation is the base. Now remember, when we have a number being raised to the exponent, we call the number, the big number at the bottom, we call that the base. So the base is the number that is going to be raised to the exponent. Now, we all know the x is what we call the exponent. So there are a couple of things that we need to know about our a, b, and x in this situation. The a, the a has to be greater than 0. Okay. The b has to be greater than 0, and b cannot equal 1. Why is that? Why would the b not be allowed to equal 1? So let's think about it. If the b is 1, what is 1 raised to the 2? It's 1. What's 1 raised to the 10? It's 1. What's 1 raised to the 500? It's still 1. There is no exponential growth or decay. It doesn't actually change the function if b equals 1. Does that make sense to everybody? If you need to pause that and kind of talk about that and get everybody clear on that, feel free to. All right. Now this is the general picture of an exponential function. Our parent function is always going to go through this point 0, 1. Okay? So that's kind of our starting point, our vertex, our, that point that we always have that we use to do transformations from. 0, 1 is going to be that point on an exponential function. So let's talk a little bit here. As always, we want to look at our domain and range of an exponential function. Actually, everybody go ahead in your calculators, go ahead in y1 and put 2 to the x. Mr. Maxwell, if you'll hit pause and let them all do that, and I want you to look at your tables. Okay, so what you should be seeing on your tables is that, as we can see on the graph itself, all of the x values will end up being a part of this graph. So our domain is all real numbers. Our y values, if you look on your table, you should be finding that the y values are getting closer and closer and closer and closer to 0, but you can't find 0 on there. So our range is y is greater than 0. Okay, again, if you need to pause and kind of talk about this as a class and help your peers understand that, please do that now. All right, exponential growth is an exponential function that models growth. As the x values increase, the y values will also increase. but the y values increase at an exponential rate instead of a constant rate like it would on a linear function. All right? So an exponential growth model happens when the b value of b to the x, when the b value is greater than 1. Okay? When the b value is bigger than 1, we have an exponential growth situation. Now, real-world example of that, bacteria grows exponentially, viruses grow exponentially, the value of a house grows exponentially. You've heard the word, hopefully, appreciation, not somebody appreciating you, but the value of something appreciating. That's what happens to a house, and that grows exponentially. But the one you guys are probably, though you may not be aware that it's exponential growth, you experience it all the time, and that's when a video on YouTube goes viral. They call it viral because viruses grow exponentially, and the views or the hits on YouTube are growing exponentially. Who knew? All right. So there are 3 words that you see very often in relation to exponential growth. Sorry, guys. In your word problems, you may just see the word growth. You may see the word increase. Or you may see the word appreciation. All of these words in a word problem will indicate to you that there's exponential growth going on. Okay? Now, don't worry about the word problems. We are going to have an entire class the next class period is going to be nothing but word problems. So we're going to go through probably 8 word problems in the notes, and then you're going to have word problems to practice. So don't stress, you're going to get your practice. And again, exponential growth happens when the base is bigger than 1. Okay? Have Mr. Maxwell hit pause if you need to get caught up and get all this down before you move on. And let's go on to exponential decay. All right, so this next one is exponential decay. An exponential function is decay when it models the decay or shrinking of something. In other words, as the x value increases, the y value will decrease. But it's decreasing at an exponential rate instead of a constant rate. Now, this is happening when b is between 0 and 1. And we are talking about it being a fraction or decimal. We're not talking about it being a negative number. Okay? As we pointed out before, the b always needs to be positive. Okay? Now, examples of decay. I don't have quite as many examples of decay, though I know they're out there. The more common ones are radioactivity. In other words, when a place gets hit with a radioactive bomb, or when a nuclear power plant has a leak, initially the radioactivity or the radioactive material is very, very high in the atmosphere, but it reduces at an exponential rate. It dissipates, it goes away. Also in in medical situations, things like when radioactivity is involved, then it will decay or reduce at an exponential rate. Also, the value of a car, that depreciates. Depreciation is one of those words that's going to signify decay. So when we are talking about decay in a word problem, it might use the word decay. It might use the word decrease or depreciation. See if I can spell that. Depreciation. Yes, that's it. Yay. And again, that's when our b value or our base is between 0 and 1, or a fraction or decimal. Okay? All right, let's see, another example that I was just thinking of are drugs in your system. Initially, when you take medication, it's high in your system. As it goes through your system, it starts wearing off. It wears off at an exponential rate. And I'm talking about legal drugs, yes. All right, so let's look at what the graphs of exponential growth and decay would look like. All right, so the graph of an exponential growth situation is going to look like that parent function did. So from left to right, it's going to go up. Okay. Now, as the numbers of B increase, so just a moment. All right, as the B values or the base increase, if you'll notice in our graphs, the steepness of the graph gets bigger and bigger. So 2 to the x is the green. So this one right here. And then as the number of the base gets bigger, it now goes up at a faster rate. As it gets even bigger, it goes up at even a faster rate. So when we're talking about the steepness of an exponential graph, we're talking about how quickly it grows. Okay? All right. Now, looking at decay, the graph of exponential decay from left to right is going to go down. All right? So this graph, or I'm sorry, this equation might look like 1/2 raised to the x. So here we've got 1/2 raised to the x is the green, 1/3 raised to the x. It is decreasing in the same way, but if you notice, it decreases faster. And then again, 1/4 to the x, it decreases even quicker. So when we talk about the base value growing, as in the growth, or shrinking, as in the decay, this is what how the graph is going to change from the parent function. Okay? If we need to pause so you guys can catch up with that, do that now.